You own a small brown bottle. It has probably sat in the back of your bathroom cabinet for years, and you have never once stopped to ask what is inside it. The liquid looks exactly like ordinary water, right up until you pour it on a cut and it erupts into a hissing white foam. That liquid is hydrogen peroxide. It is water with a single extra atom of oxygen bolted onto it, and that one extra atom is the difference between a bottle that costs about $1 and the fuel that lifts rockets off the ground. The same chemical foaming on your finger can strip the color out of hair, sterilize an entire operating theater, and push an engine toward space. Here is the part almost nobody tells you. The peroxide in your cabinet and the peroxide burning inside a rocket are the exact same molecule. The chemistry does not change between them. One number changes, and that single number decides whether you are holding a mild antiseptic or a corrosive weapon. That number is concentration. The bottle on your shelf is 3% hydrogen peroxide, with the rest being plain water. The fuel that powers aerospace engines is 90%. Same atoms, same bonds, and yet behavior so different it is hard to believe they are related. It all comes down to a single fragile connection you will never see with your eyes. Hydrogen peroxide is the simplest peroxide that can exist. Picture two oxygen atoms linked together, with one hydrogen atom hanging off each side, tilted like the two halves of a slightly open book. It is a touch thicker than water, faintly bitter on the tongue, and almost perfectly clear. Everything interesting about it comes down to that link between the two oxygen atoms. Each of those atoms is wrapped in a dense cloud of electrons, and those clouds shove against each other, straining the bond that is supposed to hold the pair together. The result is a connection that is weak, tense, and desperate to let go. Water is calm. It is stable, settled, and perfectly happy to stay exactly what it is. Hydrogen peroxide is the opposite. It is restless, always one small nudge away from tearing itself apart. When that strained bond finally snaps, the molecule collapses into two things your body already recognizes: water and pure oxygen. And it dumps out energy in the moment it breaks. That instant of breaking is not a defect in the chemical. It is the hidden engine behind every use this molecule has ever had. The foam you see on a cut is that bond breaking in front of you in real time. The whitening of hair, the bleaching of paper, the sterilizing of steel surgical tools, every one of those traces back to this same weak link letting go. A weak bond makes the molecule reactive. Reactivity makes it useful. And usefulness is the only reason it ended up hidden inside almost everything you own. If that bond is so eager to break, though, one question should be bothering you already. Why does the bottle sit in your cabinet for years, unopened and unchanged, if the molecule inside is so desperate to fall apart? The answer is hiding in plain sight, in the color of the bottle itself. Light feeds the reaction. Every ray that hits hydrogen peroxide speeds up the breaking of that bond, so the brown glass is not a design choice or a brand color. It is a shield. It blocks the light that would otherwise trigger the decay, which is why you almost never see peroxide sold in a clear container. That restlessness raises a far more unsettling question. If this molecule is reactive enough to bleach fabric and burn skin, why is your own body building it, deliberately, inside you right now? Because it is doing exactly that. Every cell you own produces hydrogen peroxide as a byproduct of ordinary metabolism. It forms inside tiny internal compartments called peroxisomes, while your cells break down fatty acids, and it appears again each time a dangerous particle called a superoxide radical is neutralized by an enzyme with a mouthful of a name, superoxide dismutase. Your immune system goes a step further and turns it into a weapon. When a white blood cell swallows an invading bacterium, it floods the trapped intruder with a burst of hydrogen peroxide to destroy it from the inside out. The exact chemical hissing on your scraped knee is the same chemical your immune system fires at infection like ammunition. But your body had a serious problem to solve. Hydrogen peroxide does not care whose cells it damages. It shreds proteins, rips apart the fats in your cell membranes, and mutates your DNA. And if it were ever allowed to pile up inside you, it would kill you. Your body responded by engineering a bodyguard for itself. An enzyme called catalase hunts down every stray hydrogen peroxide molecule and splits it back into harmless water and oxygen before it can do damage. A single molecule of catalase can destroy millions of peroxide molecules every second, which makes it one of the fastest enzymes known to biology. This enzyme is everywhere you are. It floods your blood, packs your liver, and sits inside nearly every cell in your body, standing guard around the clock. Which finally explains the foam. When peroxide touches an open cut, the catalase waiting in your blood attacks it instantly and rips loose a burst of oxygen gas. That white fizzing foam is not the chemical killing germs on your skin, the way most people assume. It is the sound and the sight of your own body disarming a threat the exact second it arrives. And this is the quiet genius that made the molecule famous. When hydrogen peroxide finishes whatever job you gave it, it leaves behind nothing but water and oxygen. No toxic residue, no poisonous film, no lasting contamination of any kind. That single trait is the reason entire industries fell in love with it. It oxidizes whatever needs to be oxidized, and then it simply disappears into two harmless ingredients. Hospitals trust it because it leaves no dangerous trace on their instruments, and factories trust it because it does not poison the water it eventually flows into. That is how one molecule quietly ended up in your toothpaste, your laundry detergent, and even inside a jar of honey. Bees add an enzyme to honey that slowly releases tiny amounts of hydrogen peroxide, and that faint, invisible shield is one of the reasons honey can sit on a shelf for years and never spoil. If it is gentle enough to live inside honey, though, how does the exact same molecule sterilize a room a surgeon is about to cut a body open inside? The answer is a ladder, and every rung up it raises the stakes. The 3% bottle in your cabinet is already lethal to the microbial world. That weak oxygen bond throws off savage fragments called hydroxyl radicals, and those radicals tear straight through the walls of bacteria, viruses, and fungi, ripping apart their DNA in a chemical assault called oxidative stress. But a bottle poured by hand can only ever clean what a hand can reach. That exact limitation is what pushed medicine up to the next rung. Researchers at University College London Hospitals Trust found that hydrogen peroxide turned into a fine vapor, paired with blue light, dramatically cut hospital infections, including MRSA, one of the most feared antibiotic-resistant bacteria in all of modern medicine. Vaporized peroxide does what a cloth never could. It fills an entire room, seeps into every surface, every crack, and every instrument, destroys the microbes living there, and then breaks down into water and oxygen and vanishes without a trace. The same molecule foaming on your finger can sterilize the room where your surgery happens. Cleaning surfaces is where the household story ends and the industrial one begins. Climb higher up the concentration ladder, and the friendly antiseptic turns into something you would never let near your skin. At 35%, the strength often labeled food grade, it stops being gentle and starts burning flesh on contact. Push it towards 70%, the range heavy industry works in, and it becomes corrosive enough to demand sealed tanks, protective suits, and rigid handling rules. At that strength, it becomes a workhorse for the planet. Roughly half of all the hydrogen peroxide made on Earth goes into bleaching the wood pulp that becomes paper, replacing chlorine and leaving behind none of chlorine's toxic residue. Wastewater plants use it to burn away organic pollutants and kill foul odors. And paired with ultraviolet light, it destroys contaminants that survive every other treatment we have. Then comes the final rung, and it is less a step than a leap. At 90% concentration, known as high-test peroxide, a single trigger on that fragile bond makes the entire volume erupt at once into a violent flood of scalding oxygen gas and heat. That eruption is not a danger engineers try to avoid. That eruption is the entire point. Force high-test peroxide across a catalyst, and the sudden storm of expanding gas becomes raw thrust, measured in thousands of pounds, powerful enough to shove a spacecraft up and off the ground. Stand back and look at the whole ladder in one glance. 3% for the cut on your finger, 35% for the food on your plate, 50% for the paper in your hands, 90% for escaping the planet entirely. The molecule never changes across a single rung of that ladder. The two oxygen atoms and their one weak bond are identical from the drugstore shelf to the launch pad. The only thing that climbs is the concentration, and riding right alongside it, the risk and the reward. The strangest part of the whole story is how quietly all of it is manufactured. Almost every drop on Earth is made through a single method called the anthraquinone process, developed by the German chemical company BASF back in 1939. It uses a recycled carrier molecule and a palladium catalyst to pull hydrogen and ordinary oxygen straight out of the air and lock them together into peroxide, cycle after cycle, on a scale of millions of tons a year. That is the real answer to why hydrogen peroxide hides inside almost everything. It is not dozens of different chemicals quietly doing dozens of different jobs. It is one molecule, built on one weak and restless bond, tuned up or down by nothing more than concentration to serve every scale of human need. The next time your eyes land on that brown bottle in the cabinet, remember what you are truly holding. The same molecule your immune system fires at infection, the same one that keeps honey from spoiling and strips the color out of paper, the same one that throws rockets toward the edge of the sky. The chemistry sitting in your hand and the chemistry roaring inside a rocket engine are identical in every way. The only thing that has ever separated the two is how much of it a person dares to use. You finally know what is inside the bottle and why one extra atom of oxygen quietly changed everything.